Hello Internet, I'm Surrendalot, and today what I'm going to be doing is making a tutorial video on how to do a pretty realistic gravity simulation in Blender. This is going to be using Python in the Blender game engine, and you're not going to need to know, in order to follow this, you don't need to know any Python at all, you can just follow it, but it helps to have a pretty basic knowledge. Personally, I'm not that experienced in Python, but I know enough to get by with this sort of thing. So, this is what it looks like, what we're going to be doing. I have a video of a bunch of tests that I've done using this method. I've optimized it a bit since then, but I'll have a link to this video in the description anyways, so you can go and check that out if you like. So yeah, we'll just get started now. So you have your default scene here. The first thing you're going to want to do is switch it from Blender Render to Blender Game. I'm going to hit Control right arrow, so we get into the the logic editing view here. And over on the right hand side, what I just went and did before is created a new text block, new script. Called it gravity, and just have the plus button. It'll say new, hit new, hit plus, and now we can start coding. But actually, before we do that, we're going to have to set up a few things first, get a few things sorted out. Over here in the scene, world panel, what you're going to want to do, it says gravity. Well, we're going to want it to be in space, and we're going to be having these objects that are seemingly huge objects. So we're going to have to turn that to 0, unless you want like a universal gravity as well as the gravitational attraction between objects, but I'll leave that up to you. What I'm going to do is change the frames per second to 24, just because it requires fewer calculations. It may be a little bit less accurate, but for the purposes of animation, it matches the standard frame rate as well. Other settings here should be fine. Now over to the settings with the object. What we're going to do is go over to the physics settings, change it from static to rigid body, keep the mass. Over here where it says dampening, we want to set both translational and rotational to 0. We don't want any of that. There's no dampening in space. It just completely destroys any sort of realism that we create. Collision bounds, and I'm going to hit convex hull. You can use box because it's a cube, but if you're using any other object, you're probably going to want to use convex hull or triangle mesh if it's a bit concave and if you want that sort of accuracy. Now, what I'm going to do is go over to, with the cube selected, I'm going to go over to the left and hit Add Game Property. Now this property that I'm going to add is not going to be a float, it's going to be a boolean, and it's going to be called has gravity. Just that, spelled like that. Has gravity, one word. The only capitalized one is the G on gravity. I'm going to check it to set it to true. One more thing I'm going to do here before going into the code is add a sensor to the cube. Make it an always sensor and hit the true level triggering pulse, which is the first button here, which means every step, every logic step, this will activate. And add a controller of Python, connect those up, and under script, add gravity. Don't mind, I have another script here called text. That's just because on my other screen I have my gravity script that I'm looking at right now because I can't remember it off by heart, so I'm going to be using that as a reference. So that's hooked up, that's good, oh, that's good. So there we go, we have a cube. If we hit P now, absolutely nothing should happen. What an amazing simulation right there. So what I'm going to do is actually hit Shift D, duplicate the cube, put it somewhere over here, and I'm actually going to just go into edit mode and scale it by like 1.5. It's edit mode. Just make sure I have that didn't, yeah, that stale is still applied. And in this cube, see all the settings and everything were copied. You can see the name changes, but the property is still there, and the logic bridge is still there. So under the larger cube, what I'm going to do is just make it a mass, maybe like twice as much. Everything just still read. So here, if we hit P now, still nothing happens because there's no gravity, there's no script, nothing is there. So, time to start writing our Python. The first thing that we're going to want to do is import BGE, which is importing all the functions necessary for the Blender game engine. Next thing that we want to do is import math. Only reason we have to do this is actually because we have a square root function somewhere in the program. We'll get to that in a bit. Then what we want to do is define, we want to figure out what object the script is attached to. So we're going to say cont, short for controller, equals bge dot logic dot get current controller. That basically says that the variable cont is the object that is attached to the Python controller that this script is in, and then we're going to say own, the owner, equals cont dot owner. Boom, no brackets on that. So now we have that set up. Now we know what the owner of the script is supposed to be. So the next thing to do is actually check to see if the object that we have here, if the owner has a property called hasGravity, which is what we set up before. So we're going to say if hasGravity, single quotes there, in the owner, and the owner's property called hasGravity is true. So if it has the property, and the property is set to true, then we can start doing stuff. So we're going to get the scene, the current scene that this object is in. Goes bge dot logic dot get current scene. We're going to set a gravitational constant. This comes in handy in the gravitational formula later on, so we're just going to call it big G equals, and it's a float number, so I'm going to call it 1.0 for now. We can always change that later. Next, I'm going to define a variable which is a three-dimensional vector, which is going to hold the force, the total force, later on that is applied to this object at each step, at each logic step. So we're going to call that total force, and the way you define this is it's an array. So you have an open bracket, 0, 0, 0, close bracket. Those are square brackets. And then the mass of this object, which I'll say is mass1 is equal to the owner dot mass. Easy enough, right? Alright, so there we go. That's what we have to do. Just gonna save that. That's what we have to do for the first section. Now, the next section here is what we're going to do is we're going to cycle through all the other objects in the scene, check to see if they have the gravity property, and then if they do, we're going to check to see how much force they exert on the owner. So in order to do that, we have to say, this is why we got the scene before, we have to say for obj in scene dot objects colon, and what that does is that it cycles through every object in the scene, referencing it as obj. So now we can use obj to basically call functions on other objects. So the mass of the other object, which I'll call mass2, is equal to obj, there it is, dot mass. Notice how it's similar to own dot mass, but it's just calling it on obj this time instead. Now it starts to get the part where we get the interaction between the objects. We need to calculate the distance, the three distances between the two objects, the x, y, and z distance. So first one is going to be x distance is equal to the obj dot world position, and then in square brackets 0 minus owner dot world position, and square brackets 0 again. So that's that, and then the y distance is equal to the OG dot world. It's the same thing, but instead now it's a 1. And now I'm just gonna, I'm just gonna copy and paste it, because what happens is that for the z distance, it's going to be, you guessed it, a 2. So there we go. Now we've got it set up that we find the x, y, and the difference in the x, y, and z positions between the two objects. So now what I'm about to do next may seem a little bit roundabout, but I'll explain it in a bit. So we're going to find the distance squared between the two objects. Now bear with me here. This is equal to the x distance squared plus the y distance squared plus the z distance squared. Now what we're going to do is find the distance between the two objects, and that's going to be basically by square rooting what we just found, which is the distance squared. So in order to do that, we're going to distance is equal to math, this is where the math function come in handy, dot sqrt, and then in brackets we're going to have the distance squared. So there we go, that's simple enough. Now, what happens if the distance between the two objects is 0? In other words, what happens if either the objects are in the same place, or there happens to be some sort of weird thing that happens, or the object is looking at itself? Well, in that case, we have to throw in an if statement right here. So, if the distance is not equal to 0.0, in that case, we can perform a calculation to calculate the amount of force based on Newton's law of gravitational attraction. So here we go, we're going to call that Fg is equal to big G, the gravitational constant we defined before, times the mass 1 times the mass 2, and then all of that divided by distance squared. Simple enough. That's the formula right there. Else, what's going to happen is that Fg is equal to 0.0. So if the distance between the two objects is 0, then the gravitational force is 0.0, because in reality it's impossible for the two objects to occupy the same point in space, and mathematically what would happen is that the force between the two objects would tend towards infinity, and we can't exactly have that. So we have to have sort of a we have to have a condition there. Next, what we're going to do is initialize the three components of the gravitational force, which will be Fx is equal to 0.0, Fy is equal to 0.0, and Fz is equal to, you guessed it, 0.0. Now what we have going on next is going to be if the x distance or the y distance or the z distance is equal to 0. So in order to solve this problem, let's say you have the both the object's y coordinates, let's say, lined up. So the x and the z ended up being 0. Well, this would end up being a problem when calculating the force in the later on a little bit, because what's going to happen is that we need to be basically dividing by the distance, and if the distance is 0, well, stuff doesn't exactly work out in that case. So here we're going to throw in if the x distance is not, where's my exclamation point, is not equal to 0.0, we can make fx equal to the absolute value of the force of gravity, Fg, times the x distance divided by the total distance between the two objects. Now, I'm just going to copy that. Oh, never mind, I'm not going to copy that. My bad. I'm not going to copy anything. Now, if I'm going to do the same thing for y distance and z distance. The y distance is not equal to 0.0. The y force is equal to the absolute value of the gravitational force times the y distance, all divided by the total distance, and if the z distance is not equal to 0.0, colon, then the f of z is equal to the absolute value of the gravitational force times the z distance over distance. Now, what I just did here is basic mechanics, and it's a formula to determine from the ratios of forces what the component of a three-dimensional force, a vector, will be. Now what we have to do is make sure these forces are the right sign. So basically, since we're three-dimensional space here, we can have a positive and a negative value for both the x, for all the x, y, and z. But since we just took the absolute value here, everything is going to be positive. So we have to look back at the original value that we got over here, the x distance, the y distance, and the z distance, check to see if they're negative. And if they're negative, and the force is not negative, then we have to make the force negative. So we'll do that by saying, for example, for the x, we'll say if the x distance is less than 0.0, and the x force is greater than 0.0, then the x force is equal to the negative of the x force. And we'll do the same thing for the y. At this point, it would probably be just easier to copy it. There we go. Change that to y, f, y, y, and y. Why, you ask? Well, because physics. There we go. So that should be that. The very last thing we have to do now, not the very last thing, the second last thing we have to do now is add these forces to the total force. So, to each component of the total force, rather. So, total force, which remember is our three-dimensional array, not three-dimensional array, three-dimensional vector. So, an array with three indices here. So total force, the first index in that array, we are going to add the x force, the second index, we are going to add the y force, and third index, we are going to add plus equals, not equals plus, the z force. And that's that. Now that's inside the loop. That's inside the for loop. So for every object that goes by, it's going to calculate the force applied by that object and then add it. Now what we need to do is, outside this for loop, we need to outside this for loop, all the way at the bottom here, all the way outside, bat at the beginning of the line, we need to apply the force to this object. So we have to say own dot apply force, and then in brackets we have the force we're going to apply, which is the vector total force, and then next is 0 because we want the force to be applied on a world scale and not on a local scale. That's how this function works. Now, looking back at this, I realized that I'd made a pretty big mistake, and that mistake is this: right after the beginning of the for loop here, before we do any of this stuff to figure out the stuff of the things with the other objects, we need to make sure the other objects are using gravity as well. So in order to do that, we have to have an if statement here. So if the has gravity is in obj, not own this time, and obj, the property called has gravity, equals true. Only then can we do all this stuff. So basically, like, so I have to re-indent all this stuff because Python is like that. There we go. That looks much better. So I'm just going to go ahead and save that. And this should work now. Although, knowing me, I'll probably get an error. So I'm going to go over here, and as soon as I hit P, these objects should start to attract each other. Well, what do you know? It actually worked. First time for everything, right? Usually I did a whole bunch of errors. But as you can see here, two objects are attracting each other, and you can tell that the object with less mass is having less, is moving more, sorry, than the object with more mass. That's because of everything in the formula. I'm not going to go into detail with that, but that's basically behaving pretty realistically. It's because now if I took this, which has everything attached to it, copied it, put it over here, scaled it up like this, and gave it a mass of, let's say, 50, and hit play. I mean, so that's not fun. Let's do a mass of 200. That's a little bit more exciting now. You can see what's going to be happening here. The large object is barely moving because it's so massive, and the other objects are being drawn to it. So you can see exactly what's happening. Yay! Physics, so much fun. Now, the one last feature that I wanted to show about this is one of the features that is kind of a side effect of doing the whole property thing, is that let's say I did not want to use this object in the physics simulation. Let's say I just wanted to use these two objects. Well, I'm not going to like delete this or put it on another layer. All I have to do is uncheck the has gravity property. And now, hit play, it's suddenly not included in any of the calculations because of this line here and this line here, which basically means that the other objects do not recognize it as an attracting object, and it does not recognize itself as an object that should be attracted. So there you have it. Now what you can do actually is take like this, for example. I'll put this back to true. You can say you can say record animation, which is why I set it to 24 frames per second before. Hit P if you want. If this is all, so if you want to make an animation out of it like I did. If you just want to do physics simulations, well, and good on you. I mean, it's fun. I'll give you that much. So there we go. We can have that. It behaves exactly the same way every time, which is honestly to be expected. The code is not optimized fully. I do not know Python that well, and I'm sure there are much better ways to do all of this, but this is the best way that I've come up with for now at least. So I encourage anyone who knows the slightest bit more Python and Blender than I do to look into this if they're curious and change stuff, and let me know if you want what you've changed and how you could make it better. Because I mean, like, as soon as I get like a whole bunch of objects, my computer starts to lag out a lot when doing this. It doesn't mess up the calculations, it just slows it down a lot, and yeah, I'm feeling like high risk of crash here. So now what I did is I played it with the record animation setting on in the game window. Now I can go hit Control left arrow, go back to the main screen, and you see now for all these objects, oh my goodness, look at all the yellow lines. So now we have it up to about 1200 frames. And now I hit play, and this is an animation. This is every single frame, the rotation and the location of each of these objects is keyframed. It's pretty ridiculous, and it can get laggy really fast if you have a lot of objects, but you don't have to run the simulation every time, and it's baked, it's set in. The only disadvantage is not only that it gets laggy, but that you have to like delete all the keyframes if you want to rerun the simulation. But I mean, there you go. That's it. This is what's happening. So you can go ahead, render this, make a nice animation, have some fun. Physics are fun, guys. So you can see how little the large cube is attractive, but it is attractive nonetheless. It's very interesting. I find this stuff fascinating. Anyways, oh, wrong way. There we go. Relatively simple code. I was surprised. So there you go. There you have it. I hope you enjoyed the tutorial. I hope you found it useful. If you have any questions, leave me a comment. I'll try and put as much information as I can in the description. I'm not going to post the code directly because I'd much prefer that people follow along with it instead of just copy it so that they actually understand what's happening. Personally, I learn the best that way. So yeah, thanks for watching. Hope you enjoyed the video. I'll try and see what I can do about making some more tests with this because it's definitely awesome. Yeah, so thanks for watching.